Welcome to this project. Today, we are gathered for us to present our project, Occupying Mars. As you have already been told, we have been split into 6 groups on the topics of infrastructure, technology, food, health, energy, and the economy. And our group has been chosen to represent the topic of infrastructure. Now, I will be talking about some basic general information about setting up a habitat, a livable habitat on Mars. And Luke will be talking about the building materials required to build up such a habitat. And Krista will talk about the overall design of the base of the habitat. And Christina will talk about some general safety features of the base. So, 10,000 people. That was the number of people we were told that we had to cater for on this desolate, dry Martian planet. So the first thing we had to do was choose a place to settle. There are a number of factors you have to keep in mind with this. First of all, the altitude. Ideally, the altitude should be as low as possible. Mars has a very thin atmosphere, so the lower you are, the more of that thin atmosphere you can use. It should also be flat, because that helps with landing rockets on Mars. And ideally, it should be on the northern hemisphere of Mars, because due to the fact that Mars does not orbit in a circuit, orbits in a sort of oval shape, in the northern hemisphere, the seasons are a lot milder. Based on these features, we chose to settle in the northern Amazonas Planitia, where there is that red arrow on the screen. This has an average elevation of around 3.8 kilometers, so it's very low. It has a lot of water in ice in its regolith, which is the name for the soil on Mars, and which is good for extracting water, as I will talk about later. And it is close to the mountain range Olympus Mons, which indicates that there are tubes called lava tubes that are helpful in extracting out the colony, which Luke will go into much more detail later on. So the next step we had to look into was how much space we needed for this colony. So what did we do? We looked to real-world cities to look at how much into how dense people tend to be packed in real-world cities. And there are a few examples over there you can look at. But after looking at what other people have thought of because we are not the first to think of designing a Martian colony, we have decided to go with 128 people per hectare. A hectare is a 100 meter by 100 meter space. So for 10,000 people, that would require 78 hectares, or just under 1 square kilometer. But that's not the only living spaces that these people that will live on Mars will have, because the farming sector also requires land, a total of 190 hectares. 80 of these hectares are garden spaces that the humans will be allowed to walk through. So in total, that gives 158 hectares of livable space for the people who will live there. So for a total habitat of 268 hectares. So extracting water. There are 2 main ways of extracting water on Mars, one of which I will talk about myself, and another will be talked about by the other teams. This is the simplest of the 2 ways of extracting water, but it does not yield the most. This is extracting water from the regolith or the Martian soil. The soil on Mars has pockets of water ice, which you can heat to evaporate the water, which you can then collect and condense to get liquid water. Also, there are pockets of certain elements and compounds like iron oxide, which are hydrated salts, which means that they are bound to water molecules. If you heat these even further than the boiling point of water, you can separate this water, called water crystallization, from these compounds, and you can extract it alongside the water ice. And this can be used, of course, for drinking, watering plants, and a variety of other uses. I now leave it for Luke to talk about the building materials we will need.
So, the key to building so far away from Earth is to use what you have available as much as possible. So the base will be mostly underground for very easy radiation shielding. But obviously not all of it can be underground. For example, farms need sunlight, green spaces also need sunlight. So behind me, this is basically radiation shielding that can be sandwiched in the domes in between the layers of glass. This should absorb most of the radiation, most of the neutron radiation, electromagnetic radiation is negligible, and so on. So, silica aerogel, it's like fiberglass. You can make it by processing silica, which is sand, with a special process. It's placed on the top and the bottom. It will work as insulation, which will make the domes more energy efficient, as obviously you won't need to waste as much energy heating. Boron nitride nanotubes can produce them on Mars as well. You can mine boron from boron-rich clay. And also there is a small amount of nitrogen in the Martian atmosphere as well. With another specialized process, this can be made into boron nitride nanotubes, which is a transparent material that should absorb a lot of neutron radiation. Hydrogen-based plastics, for which we have chosen to use polyethylene, which we use nowadays as well. We can process ethanol to make this. Ethanol, we can get it from other processes as well. And this will do something similar to the boron nitride nanotubes as well. The bottom layer of silica aerogel does, as I said earlier, it will provide a lot of insulation as well. Now, what I was saying, by putting the base underground, we can minimize on building a lot, as obviously if we dig, it's going to be more efficient. And to add on that, if we place the base, if we start it from a lava tube, which is basically a cave left over from when Mars was volcanically active, we already have parts of it dug out for us. So we can dig out when we need more space, and this will reduce the costs we need to pay for all the digging. In terms of materials we can use for building, we can use Martian basaltic rocks, which are not dissimilar from basalts we have here on Earth. We can use them just like you would use normal stone, and we can also 3D print them, so we can automatically build buildings whenever needed. Sulfur concrete, basically this can be used as a backup for when we don't have any basalt and something needs to be done quickly. It's basically a mix of 50-50 sulfur, which acts as a binder, and Martian regolith. This has good compressive strength, but thermally it doesn't fare so well, as it will start to deform under heat. For the buildings as well, we can use algal walls, which will produce oxygen and will add some greenery to the buildings on the inside. Now, we will discuss more in depth the habitat as a whole and its structure.
Hi, my name is Krista, and today I'm going to talk to you about how our ideas came and why they are there. Before we start, think in your head, if you had to design a structure on Mars to hold 10,000 people with all their necessities, how would you do it? Our team decided to go with domes, as these can retain the pressure and will also prevent heat from escaping, which will save us on our energy. And as a final draft, we came up Let's start with overground. As you can tell here, we made a long tube with a dome on top. Now know that all the structures outside are made with the radiation protection, which we said before. Inside here will be the main area for the plants, which will then go into different sections. Here for specialized plants and here for animals, which will be spoken about later on. We also have an area which will be like a large garden, which will include flowers, bees, and trees. So similar to Earth. If you ever want to go on a walk through a garden, go there. And we also have a place just for chocolate because it was voted by majority that chocolate is needed on Mars. For an astronaut to enter inside, there will be an airlock, which the astronaut will go down into a cleaning zone, which will also be spoken about later on. And through this zone, you could either enter into the lab, as obviously research will be needed to be done on Mars, or into the actual living space. Families will live on different layers in capsules, which will include washrooms. On each layer, there will be a food area, and every 2 to 3 layers, there will either be a clinic or a hospital. We will also have schools, as if you are going to have a colony, there will be children. There will be places for entertainment, gyms, sports, and also places for relaxation, religion, and meditation. And there will be places for meetings. And as an economy, you can't expect there to be a zero criminal rate. So down here, we design a prison which will have a gate guarded by security. And for health, if you ever want to go in a place which you can actually feel the gravity, we have designed spinning therapy, which Christina will talk about more now.
Hello, my name is Christina, and I'm going to be talking more about how we're going to keep our Mars base safe. So, first of all, I'm going to be talking about the Mars dust. So, one of the main concerns that you have to take into consideration when building a Mars base is the Mars dust. The Mars dust contains various toxic chemicals such as percolates, which if we breathe in can cause several health problems. To combat this, we're building our airlocks with, as you can see in the diagram, a suit port. So in the diagram, you can see an astronaut entering the spacesuit through a suit port. This means that the spacesuit won't actually go inside the base. So how this works is the astronaut climbs in the spacesuit via an opening, which can be seen from the inside. This works in the same way if you want to go inside the airlock. This would prevent our Mars crew from bringing in harmful Mars dust into the habitat and contaminating living areas. Another major concern is Mars dust storms. Even though Mars dust storms aren't as extreme or violent as Hollywood depicts in certain movies like The Martian, they're still very disruptive, long-lasting, and can also damage our machinery as well as our base. To prevent this, when designing our colony, we made use of various dome and slope structures. We're also constructing our airlocks with dust capturing systems like vacuums, electrostatic filters, adhesive mats, and magnets. We're also creating electrodynamic screens, also known as EDS. So if you see on the PowerPoint, it shows a schematic view of an electrodynamic screen. So how these work basically is the dust will fall on the screen and the dust will get charged. Then this dust will get swept away by a traveling electric field created by the screen. These screens will be attached to our solar panels as well as the exterior surfaces of our base. Finally, a major concern on Mars is Mars's reduced gravity. As you may know, Mars only has 38% of Earth's surface gravity. This reduced gravity can lead to various health problems, such as cardiovascular problems, muscle wasting, and reduced bone loss, which will be talked more about later by the health team. But to prevent this, our astronauts will have to work out daily. Thankfully, our colony is equipped with a state-of-the-art gym with resistance training machines that simulate Earth's gravity. A more complex and long-term solution that we've also developed are rotating chambers. So these are basically rotating rooms that simulate gravity by creating a force that pushes everything outward. Don't worry, if you use this, you won't feel nauseous or sick, because we're going to try to build this as big as possible, because the bigger it is, the less fast you have to spin. So in conclusion, everything that we have said makes sure that we're going to have a safe, secure, and spacious home on Mars. because the future is now. Thank you for listening.